My name's Amy. This is Casper, Joshua, Alvaro. Welcome to the Flexure Lecture. First, brief introduction about myself. My background is in mechanical engineering. That's also what I do professionally. But probably like many of you, I spend a lot of time on personal projects outside of work, and that's really been like my main arena for discovery and learning of lots of things. And that's really where I found Flexures to be the most useful for a whole bunch of projects. So while there are people in this world who study Flexures very rigorously and perhaps academically, I am not one of those people, but I will be referencing a lot of their work today. I'm going to try and present stuff maybe from a more practical perspective, and so hopefully you still find that interesting. So, roughly what we'll go over today: look at some examples, talk about design trade-offs, some manufacturing considerations. We'll go through a whole bunch of examples, and then, as I said, we'll end with assembly of some Flexure girders. First off, what is a Flexure? Wikipedia says Flexure is a flexible element or a combination of elements engineered to be compliant with specific degrees of freedom. So we have here compliant, something that's going to be soft, deformable. If we want to be able to use it as a useful mechanism, it's got to be able to do that lots of times. So often you'll see springs come up a lot today. So we'll talk about what is a spring. This chart might be familiar to some of you. This is a StressStrain Chart. Stress measured in force over area, strain as a percentage of elongation. These charts are often taken by taking a dog bone sample of this shape and then pulling on it and measuring the force in deflection over that time. This is kind of a cartoon of a stress strain curve for, I think this is carbon steel. So you'll see, so for example, let's see. So the region here that we're most interested in today is this elastic region where the relationship between stress and strain is fairly linear. The slope of this is called the Young's modulus, also often known as stiffness. So for example, you could imagine if we took a point here, a material that for the same force over area deflected a lot less than the line that we here, that would be a stiffer material, right? Let's keep building our intuition around that, because I think it's nice when we can turn graphs and kind of internalize them as an intuition. So here we have a comparison between a brittle material and a ductile material. Brittle material is something like ceramic, that, you know, when you apply force to it, you're not really detecting very much deflection until suddenly it breaks. Where a ductile material may be something like a mild steel or a copper, where you're feeling it's like fairly stiff, and then it starts to deflect, and at this point, the deformation in it becomes permanent. And even as you're permanently bending it, it's still providing some amount of force. It's still like providing some amount of force resistance, and then it breaks. Here's another cartoon of various comparisons of different materials: rubber, aluminum, steel, and glass. So it's cool at this point to think about, like, what is it that makes materials stiff? So there's materials like on a atomic or molecular level are bonded in certain ways, different. So with a steel, for example, as you're stressing the bonds between the molecules, you may be able to kind of pull the bonds apart a little bit, but they're strong enough that they'll snap back together. And that's essentially what's making a really good spring, is something that you can put some deformation into it, but as soon as you remove the deforming force, it will go back to its original shape. This is some curves here of a material called Delrin, which is what all the kits are made of today, and a lot of the demos are made of as well. And so this is as it varies through temperature. This is for 23 degrees Celsius all the way to 100 degrees Celsius. And what you can see here is that the amount of the linear region that we have to work with, the elastic region that we're so interested in, is, to begin with, quite small for even a room temperature cell ring, and increasingly smaller for plastic when it warms up. And so like plastics are these like long polymer chains, and they're kind of like weakly bonded together, and so as you kind of stress them apart, they're sort of like wet spaghetti. Like they might actually pull apart from each other and then stay in that shape and not really want to come back. So plastic, you might have already heard, will creep. And creeping is when plastic is sort of sustaining a force for some prolonged period of time, and then it sets into that shape. So anyway, just cool things to consider when we're designing for compliance or for spring mechanisms using plastic and really any other material. One last boring slide. This is how we characterize springs. So the force that you apply on a spring is linearly proportional to the amount that you deflect it. This is like why like spring scales work. For a cantilevered beam, this messy thing here is essentially the spring constant. So here, E is the Young's modulus, the stiffness that we just talked about, material-specific property. This is the width of the diving board. T is the thickness, L is the length. And this also makes sense too, right? These two are the dominating factors when it comes to what's affecting the stiffness of the beam. Makes sense. If you were to make this a little bit thicker, this would be much stiffer to deform. At the same time, if you made this many times longer, it would take much, much less force to deflect the end of this beam by the same amount. That make sense? Great. So we love it when our intuition matches equations. Okay, so let's look at some examples. Here we have like a ketchup lid, Tupperware. This here are the leaf spring shock absorbers on a truck. So on all these examples, what I think is fun to think about is which one of these is a spring force like never needed, or momentarily needed, or always needed. So for example, maybe on a lid or a Tupperware like this, you don't actually need there to be any force in the bending mechanism. I think a book is also a good example where like you don't really need the book to like spring open or spring close. You just need it to be able to deform. Whereas for something like this buckle here, as you clip it in, you want there to be like spring force for a moment, but then when the buckle is sort of in its clasp state, you're not really relying very much on the mechanism like applying force to anything in order to function. And so that's cool to think about, like why it makes sense then to make this out of plastic, because it, as I said earlier about the creep, it's not experiencing like a constant load, and that's what's going to make it mechanisms that will have like a longer, like usable lifespan. And this here is another example of like, in this particular use case, I used it for kind of completing the body of the ukulele. For sometimes people use that as like a living hinge, but in this case, like I want it to bend once and never again. So maybe that doesn't count as a flexure once you've glued it in place. Here are other examples, maybe less around us than the previous slide. Ring clips. These are flexible shaft couplers that allow for axial misalignments. And this is a precision locating stage, so as you like move these thumb screws, you can kind of move this very precisely. This is an example I'll talk a lot more about later. It's one of my favorites. It was designed for a 2-axis thruster for a satellite. And then this, hopefully this is like less all around us, but another common example. This is probably an example of flexures that are the most around us these days. The kind of Mem structures that are used in accelerometers or gyroscopes. So this is a cartoon of how that works. You essentially have these spring members here that are suspending mass, and as that mass travels back and forth, the capacitance between certain things will change, and you measure that, and you can measure things like its acceleration. So this is like the real world version of what that would look like. And I think this here is a chip that's really similar to the first gyroscope that was shipped with the iPhone 4. Okay, so now we'll get into more design trade-offs. First, I want to plug this research group. A lot of the GIFs you'll see here I've borrowed from their website. They go through kind of these trade-offs in a slightly different order than I do. I think it's still valid. I prefer to think about it this way, but anyway, lots of great resources there, lots of things that you can like download and 3D print yourself, so a fun place to visit. Okay, so first off, often with Flexures, there's an opportunity to make mechanisms that are much simpler. So this vice grip, for example, if we count the parts, you have minimum 1, 2, 3, 4 parts in addition to a whole bunch of pin joints. Whereas this example over here is one piece of plastic that essentially has all of the same motions that this one does. So lower part count, you don't have to worry about like friction between any of the joints. There are conditions where it would be much more reliable. This is another example of a like one-piece door latch. I think people have brought up before that there are simpler ways to do a door latch that's still a flexure. This came from a lab that where I think they built a tool where you can have like a matrix of like kind of flexure pixels or like rigid pixels, and you can kind of input a desired output motion and an input motion, and it'll kind of like calculate which one should be rigid and which one should be flexible in order to get that output. So anyway, cool. It's still a cool effect. Here's that thruster thing that I talked about. So in the middle, you have a 3D printed titanium compliant structure. There's these two input motors which give you 2-axis control of this thruster. And this, I think, is a really awesome demonstration of a lot of the benefits of compliant structures. Here you have something where if you did it with traditional mechanisms, you would need gears, bearings. It could end up being quite heavy. It could end up being larger. Both of those are obviously constraints for launching satellites. And so yeah, like with the vice grips from the previous slide, there's an opportunity with Flexures to really shrink down mechanism designs. This one also has the added benefit of providing really precise motion. So if you don't have bearings and gears, you don't have backlash, which is like kind of slot between mechanisms. You really just have that one structure. So lots of benefits here. Potentially a downside to certain flexure mechanisms is that, because you're deforming a spring, there's times where you're like putting, as you travel further into the range of motion, you have to apply more force in order to get there. That's not true with like a pin joint. The pin joint, you can rotate to any point of it. It's like essentially the same force. So with this one, I don't know if that's an issue for them. Like if the motor wants to turn more, there's the power you have to put into the motor is comparatively more. But I think that there are some cases where obviously you can use that to your advantage. So just depends on your design application. Here are some examples where we use that to our advantage. This top part here is part of the tool changer mount that Joshua designed for his 3D printer Jubilee. And so here you can see there's a compliant structure there, and it not only provides a nice lead-in, it provides like a constant gripping force. This is an example here where this is part of like a linear rail structure. The bottom part of this beam not shown has rigid rollers, and the top beam here might not be perfectly parallel with the one before. And so it's hard to see, but this beam bends very slightly as it travels, and so you're relying on the compliance there to make sure that the mechanism works well. And then finally here, this is another example from Joshua of a pen holder. Imagine this one like turned 90 degrees. And you could put a pen in there. And here you might have it so that the actuator that's pushing the pen down is only actuating in one direction. and then maybe the retract, you can just get that from a spring, or the spring compensates heavily for the amount of retract force needed. Okay, so there are downsides to flexures. You can imagine that if you had a really complicated flexure, like that satellite thruster example, or if you were going to push a material to kind of its property limits, or if you wanted a flexure that's going to last many, many, many cycles, then you might have to do some pretty complicated simulation work in order to verify that that's the case. I do basically no simulation in any of my personal projects, so it's all guess and check, trial and error. So yeah, that can be quite a burden for designing flexures. One of the main reasons for simulation is to avoid things like fatigue. So this is a pretty generic fatigue chart, but in general, like the number of cycles that something can survive, there's a relationship to kind of the amount of stress, the percentage you get up to the yield stress that you subject the material to for these cycles. So for example, if you push something like very lightly, you can go many, many cycles without it breaking. If you push something much closer to its yield strength, you might not get so many life cycles out of that. So with fatigue, because the bending comes from the deformation of the material itself, this is a major concern. And of course, there's limited range of motion. In some applications, that's obviously not an issue, but obviously, like, none of these you're going to get 360 degrees rotation with. So sometimes flexures just don't make sense. Okay, but for DIY project purposes, I think that there's a lot of great benefits. So a lot of the flexures that I've shown are essentially two-dimensional shapes, and that really makes a lot of DIY options possible. First off, you can just start with sheet material. So for example, this is a brake for a kick scooter that I built, and the spring here is literally just a little strip of polycarbonate, and that's enough. Really easy to laser cut. Maybe some of you saw this already. We can play around with it more today. 3D printing, for example, like this one here. And then if you're lucky enough to have access to a water jet, there's lots of different shapes you can make that with that as well. Another main manufacturing benefit, I think, is that with flexures, because flexures can kind of like be compliant and take up like a range of space, it can make your projects like doable, like basically just more robust to crude processes. So this is an example here where maybe you want a really tight, snug fit to these precision shafts here, but instead of like calibrating your 3D printer to be just perfect, to be the right size, or instead of like investing in reamers or like precision tooling to make an exactly right size hole, you can have some compliant members here that maybe will just take up the slot for you. Sometimes that doesn't provide enough force, but in a lot of cases, that's sufficient. Another way that they're robust is that for processes like, really like all three of these, you get really high accuracy, like point to point feature-wise, but because of the kerf of the material, so if you look at like laser cut parts, you'll often see that, and you'll see that with the parts that I'll hand out today, that the edges, the cut edges of the parts are not perfectly perpendicular with the tops and bottoms. So you might get some variation in like the thicknesses of materials, but the relative thicknesses of everything is like pretty consistent. So if you cut the shape out, you know, you might not get the exact thickness you want here, but that thickness will be pretty close to the thickness of the opposing spring that it's working with. So if you want, you can just sort of like punch out a bunch of parts, maybe with small variation to thicknesses, and then just pick the one that works best for your application. Let's see. Here's another one of my favorite examples of how it's robust. So this was a snap lock mechanism that I first learned about from the MIT machines that make snap lock thing, which I think a lot of this was later, the ideas were applied to the other mill. So here you can see this feature is used as a close fit locating feature, and then these two arms here are flexures that kind of, because I've designed in an interference here, it's sort of applying a load that's compressing the joint together. And so that's a way of using not very precise tools to get like a very precise and consistent locking feature. This also, I think, is a really common one where for two linear rails, to correct for them not being perfectly parallel, you have one that's fixed and then one that has a little bit of compliance in it. These are more, this is like the ugliest slide, sorry. These are more examples. This is, I bought like a mesh network for my house, and it comes with this thing and a long cable, and so if you just like have it plugged into a wall, you have random stuff just sitting on the floor. So this is an example of one where I'm not really relying on the spring of the material itself. I'm just using zip ties to keep everything tight. This one I saw like yesterday, and I just really liked it. This is the mud guard on a big semi-truck, and I imagine like this thing is quite heavy as the truck is driving along, and so there's probably a lot of stress in this joint here, and they're probably trying to avoid like fatigue happening on this particular joint here. And so by putting this structure in, they're essentially spreading the deformation along a much longer length of material, so the percentage strain across all that material is much less than if it only had that little joint there. So I just think it's a cool use. Okay, finally, just a bunch more resources that I think are really cool. This is a great video that the YouTube channel Veritasium did. They basically took a tour of this lab. It's pretty fun to watch. Larry Howell is a professor from this research group, and he and colleagues have basically written the books on compliant mechanisms. So if you really want to dive into that, those are great resources. But minimum, I think watching that video is great. And I'll post all these slides somewhere on the internet. So. Okay, so this brings us to the thing that we're going to assemble today. This was inspired by maybe before we get to this, I'll pause on this for a second. I have a whole bag of toys. I'll talk about them, and then I'll talk about this, and then we'll pass everything out. Does that work? This is the thing that we're making today. So I don't know if it's hard to see, but essentially like the fingers are deformable. So anyway, we'll make these later. You may have seen me with this yesterday. So this is a demo board with a whole bunch of flexures on it that I really like. This is a butterfly flexure, which mimics a pivot, and you can kind of push on it. It's like pretty stiff in other directions, but this one, yeah, pretty close to a pivot. This is a slide, you see pretty commonly. This is kind of a tab that rotates out, and because of this flexure, it locks. This I used on a frame, a wooden frame, to hold an iPad in the moonroof of my car. So the tab like slides out and like locks into the gasket of the car window. This here has a disc with detents, and then also some toggle switches. This I actually designed to make sure that my cat doesn't get overfed. So this is like days of the week and he gets 2 meals, so we don't get confused. This is just a simple ratchet, makes great sounds. This one here, it's hard to see, but when you get it up close, you can take a look at it. They're 2 holes, but there's a compliant structure in each one. And so this is just to show that it's a good way to, let's say you have like a bunch of motors or parts or sensors or whatever that you want to hold, and there's some variation across all of them. You can just design an interference fit, and that interference fit is probably enough to take up like the variation in your part tolerance. So that's an example of that. This one, I designed the springs so they're a little bit too stiff, but if you look at it, there's 2 deformable structures in here. One of them is thinner than the other, and you'll see that reflected in the force that it takes to pull them apart. Much less perceptible is that the detents are actually of varying depth, and so if you're like very slow and careful, you can detect like a difference in force as it takes to push them in and out. But I won't be surprised if you can't detect that. This is that very satisfying toggle switch that I showed from BYU. This is the printed version. I don't know how long these will last, so this is like fatigue playing out in real time. This is the laser cut version. It was the laser cut version of the same thing. What else do we have? Oh, this is an example of the this feature here. Actually, this is that part. So I'll take, there's a fan blade on it so that you can spin it. I'll take that off for now. If you want, I'll even take that off. I made this to clip onto my hat so that I could walk around like a nerd. But yeah, you can feel free to snap this together. This is a, hopefully this one will last. This is a 3D printed like bistable mechanism, also from BYU. So it's printed in this state, and then you can pull it like that. It's also very satisfying clicking sounds. Okay, I think that's all. Hopefully they last long enough. Okay, talk about this. The main thing that I want to go over here is that I'm using these push rivets to put everything together, so there be no tools are required. The rivets, however, though, have this fillet on the underside of the head. And so if you look at it, certain parts, namely these two link shapes, and then only one of these body shapes has laser etched counterbores. And the purpose of those are to provide clearance for these fills. I'm pretty sure the things will still work if you put them in backwards, but they'll just work much nicer if you have them in the right way. So when you get your parts, make sure that you're looking for those, and that's the side that the rivet head goes to. Finally, the rivets have these teeth on them, so they're only locking like incrementally, and because the thickness of the materials that I'm using, I couldn't get it to lock exactly at the right increment for these. So there are washers that are included to add up to the right thickness stack. So put in this rivet, do whatever stack of materials, then make sure you put a little washer on it. Again, if you forget the washer, it's still gonna work. It'll just work nicer with the washer in place. Yeah, these are the assembly instructions. We pass out kits. Hit me with questions.